In this video, I will be introducing the idea of rational functions, and then we're gonna learn some characteristics of these types of functions, and then we're gonna learn how to sketch rational functions. So here are the list of objectives. So finding domains of rational functions, find the vertical and horizontal asymptotes of these graphs, sketching rationals, and then maybe using rationals to solve problems. So what does a rational function? So basically, it's a quotient of polynomials where you have some n of x divided by d of x, where n of x and d of x are both polynomials, and bottom is generally is not zero, because if it's zero, then this fraction will be undefined. So we always have some polynomial at the top, some polynomial at the bottom that is not zero. In general, though, the domain of rational functions of x includes all real numbers except x values that make the denominator zero. So that's the key thing. We're going to make sure that the x value that we think for the domain is not going to make the bottom zero. Much of the discussion in this chapter is going to focus on the graphical behavior near the x values excluded from the domain. So here's an example. Find the domain of f of x equals 1 over x and discuss the behavior of f near any excluded x values. So we're going to think about the domain of this function. So the domain of this function is going to be all x's except what makes the bottom 0 is x equals 0. For that reason, domain is every real x value except for x equals 0. So to determine the behavior of the function near this excluded value, what we do is we evaluate the function to the left and the right of x equals 0. In other words, we're going to get super close to 0, but we're not going to be quite there yet. So for the first table, you guys realize that we tried some values. So like say if x is -1, then function, because the function is what? F of x equals 1 over x. So when you evaluate that f -1, you get 1 over -1, which is -1, right? So doing that similar thing for all these x values, we get different y values. But you guys realize as we get closer to 0, the bottom seems to be getting smaller and smaller. In other words, the number is going to look bigger, right? So it's going to be like -1 million at some point, but still the x is never going to touch 0. Similarly, for the other side, when we get closer to 0 from a bigger value, say we started with 1, when x is 1, y is 1, when x is 0.5, y is 2. You guys realize as we get closer and closer, as we put bigger x values, the function f of x seems to be getting bigger, right? So it looks like the function is always getting bigger as x is getting close to 0. So for that reason, we're going to say that as x approaches to 0 from the left, f of x decreases, and in contrast, if x approaches 0 from the right, then the function increases without a bound. So we can tell that by looking at the actual graph, where you guys realize when x is getting bigger on the right, so when you put like bigger and bigger x's, the function, the y value, you guys realize is, I'm going to show that with red mark, the y value seems to be getting smaller and smaller. So as x is going to get bigger, y is getting smaller. And then as x is going to the left side, so let me use that different color for that. As we do x smaller x's, so like -5, -50, -5 million, right? We're going to realize that the y value here is going to get bigger. It's going to get towards this side. So for that reason, f of x always increases. So this also explains a little bit about that, but that the value that we exclude is x equals 0. So what we're gonna call that value from now on is gonna be a vertical asymptote. So points like these where function either goes to positive infinity or negative infinity, the y value of the function always increases or decreases, is always going to be vertical asymptote. And this is kind of a unique situation for generally rational functions. All right, so here's the definitions of vertical and horizontal asymptotes. So the line x equals a is a vertical asymptote of the graph of f when function goes to infinity or negative infinity, as x goes to a either from the left or the right. Similarly, the line y equals b is a horizontal asymptote of f when f of x gets closer to a value b, this is a value, it's a y value, as x increases or decreases. So we're gonna take a look at that on these figures. So you guys realize on the left hand side, as the x's are getting bigger, the y values are getting closer to this value 2. So then horizontal asymptote must be 2. Similarly, for the curve on the left, as x is getting bigger, the y value is getting closer to that y equals 2 thing. So same idea on the one in the middle. You guys realize that there is a horizontal asymptote y equals 0 because the curve is never going to touch the x-axis. And then on the right, on the picture on the right, realize part B doesn't really have a vertical asymptote like A did. And let's take a look at part C. This guy has both vertical asymptotes and horizontal asymptotes. Vertical asymptote is x equals 1, and then horizontal asymptote is y equals 0. So generally, you can tell vertical asymptotes and horizontal asymptotes by looking at the graphs. That's one way of doing it, but it's not as accurate. So for that reason, we need to know how exactly find vertical and horizontal asymptotes. So the way we find that is this definition. So vertical and horizontal asymptotes of a rational function. So how do we exactly find them? So here we're going to define a general rational function. So let f of x equals n of x divided by d of x be some rational. It could be anything, right? It could be any rational, it could be any polynomial. So these guys are my polynomials. Polynomials. So then polynomial at the top has the a sub n times x to the n, where a sub n is the leading coefficient, b sub n is also the leading coefficient for the other polynomial. And then n and m are the degrees of these polynomials. These are the degrees of the polynomials. So according to our rule, the graph of f has vertical asymptotes at the zeros of d of x. What that means is x's that makes the bottom 0 are going to be the vertical asymptotes. That's always the case. So the way we find vertical asymptotes is we find x values that makes the bottom polynomial 0. The next rule is for horizontal asymptotes. So that one has a little bit condition. So the graph of function f has one or no horizontal asymptote by comparing the degrees of n of x and d of x. So realize the degree of the top polynomial is n right here. The degree of the bottom polynomial is m. It's right there. So if m is bigger than n, so in other words, the degree of the bottom is bigger than the degree of the top, then always the line y equals 0, which is the x-axis, is always going to be the horizontal asymptote. So you guys realize the function we previously had in the example 1 over x, this function, has the horizontal asymptote to be the x-axis because the bottom degree of the bottom polynomial is bigger than the top polynomial. Secondly, if they have the same degree, So the degree of the top is the same as the degree of the bottom. Then the graph of f has the line y equals a sub n divided by b sub n, which is the ratio of the leading coefficients, is going to be the horizontal asymptote. Lastly, if the degree of the top is bigger than the degree of the bottom, then there is no horizontal asymptote. So we're going to note that if the degree of the top is bigger than the bottom, no horizontal asymptote. So here are a couple of examples. So for the part A, you guys realize n equals m because they have the same degree. So we're going to say, well, then y equals a sub n over b sub n must be the horizontal asymptote. So the way we're going to do that is we're going to take a look at the leading coefficient of the top, which is 2. Leading coefficient of the bottom is 1 because it's 1 times x squared. So 2 over 1 is 2. So y equals 2 is horizontal asymptote of part A, right? Of part A. So how do we find the vertical asymptotes of part A? The way we're going to do that is, I'm going to do it on the right side. So for the vertical asymptotes, we're going to make the bottom 0. So x squared minus 1 equals 0. We're going to find x values that makes the 0. So I factor. It's almost like solving or finding zeros of polynomials. So it's going to be x equals 1, and then it's going to be x equals negative 1. So I'm going to find two vertical asymptotes for the part 1. And you can find the explanation on the following slides. When you graph that first polynomial, you're going to realize its graph is going to look like this, where we found two vertical asymptotes, x equals 1, x equals negative 1. And then we realize that it has a horizontal asymptote at y equals 2, which is exactly what we just did find. And then graphically, you can see how all that plays out. For the other example that we were given, you guys realize part B had this like a little bit more complicated function, which isn't too bad. So we're going to take a look at the degrees. You guys realize the degree of the top and the degree of the bottom is again same. So then we divide the leading coefficients. So like y equals a sub n over b sub n, which in this case seems to be 1 over 1 because it's always 1 times x squared, 1 times x squared. So y equals 1 must be the horizontal asymptote. So now we're going to find the vertical asymptote. The way we're going to do that is, again, we need to make the bottom 0. One thing we need to make sure with these polynomials is that we simplify if possible. So I'm going to factor the top, factor the bottom. When we do that, we realize the bottom is x plus 2 times x minus 3. The top is x minus 1 times x plus 2. And then we're going to realize that we have the same factor at the top and the bottom, so we can cross those out. The function looks like x minus 1 over x minus 3, where x is still not negative 2 because this guy is a factor of this. So like when you make the bottom negative 2 in the first place, it's always going to be 0. So that's the case, and then we left out with this function. So now we're going to say, well, x minus 3 equals 0, x equals 3. So then x equals 3 is the only vertical asymptote.